record this class. So class is recorded now. And anyone is ready can go ahead to present. We have 7 people.
I want to present 4.84.
Okay.
An example, what percentage of I detective lots does the purchaser reject? Find it for I equals 1 and I equals 4. Given that a lot is rejected, what is the conditional probability that it contained 4 defective components? So we want to find the probability of 4 defective given lot rejected. So P for I equals 1. So the P of accepted is 1 choose 0 times 9 choose 3 over 10 choose 3, which is 7 over 10th. And then for probability of rejected is 1 minus the probability of accepted, which is 1 minus 7/10, which is 3/10. And then for I equals 4, example IA is in the front, on the top of the problem. So for I equals 4, the probability of accepted is 4 choose 0 times 6 choose 3 over 10 choose 3, which is 1/6. And then the probability of rejected is 1 minus the probability of accepted, which is 1 minus 1 over 6, which is 5/6. And hence the probability of 4 defective given lot rejected is 5/6 times 3/10 over 5/6 times 3/10 plus 3/10 times 7/10, which is 75 over 138.
Great job.
Thank
Very
you.
nice. Okay, anyone has any questions? Okay, that's nice work.
Hello.
Hello.
All right, so doing 4.66. So customers enter a supermarket located on a busy street at a rate of 2 every 3 minutes. And for A, what is the probability no customer enters supermarket between 7 and 7:06? And what is the probability that at least 5 customers enter during this time? So we're just doing probability, Poisson probability. So for A, between 7 and 7:06, we're going to have a rate of 4 people in that period of time. So our lambda is going to be 4. So we do P of X equals 0 for no people entering, which is just e to the power of -4, which is approximately 0.018. And then for B, we're looking at for X greater than or equal to 5. And so writing out the entire calculation, come to a value of 0.313.
Okay, that's a question for Poisson distribution.
Yes, Poisson.
Yeah, okay, thank you. Okay, that's all there is. Who's next? Anyone wants to go next?
Can you
Okay,
see
it's up. Okay. 77.
I cannot move my mouse. Just give me a second.
Okay.
Oh, okay. So an interviewer is given a list of people she can interview. If the interviewer needs to interview 5 people, and if each person independently agrees to be interviewed, with probability 2/3. What is the probability that her list of people will enable her to obtain her necessary number of interviews if the list consists of part A 5 people? So we first of all interpret the information. For the people agreed to be interviewed, we have probability of 2/3. So, and the component will be 1/3. And the rundown variable is the number of people to be interviewed, and also be the number of success. If a person is accepted to be interviewed, that will be success. And the N be the number of people in the list. So that also represents the trials. And part A, we have part A, we need to interview 5 people. So X is equal to 5. And then on the list, we have 5 people. So N equal to 5, X equal to 5, which is use the binomial distribution. That's the answer for part A. And for part B, we have 8 people on the list. So instead of N equal to 5, we have N equal to 8 this time. Oh, not this one. Here. N equal to 8. Let's do C and D first. So, what is the probability that the interviewer will speak to exactly 6 people? So, with the condition in B, so there's 8 people in the list, and we're looking for 6 success. So we have N equal to 8, and then X equal to 6. We plug into the formula. We got this for part C. And similarly for part D, we only calculate the C. For part C, we only calculate when X equal to 6 because it mentioned exactly. Also for part D. And for part B, since it didn't mention exactly, so we consider the situation when X equal to 5, X equal to 6, X equal to 7 and 8. That would be this one. That would be this one, add this one, those 4. The sum of 5, 6, 7, 8, sum of those 4 would be this one.
Nice. Yes, I like what you did in the beginning to interpret the information in the list. I think a probability questions is like that. We really have to understand the setups to draw the information and put the right notes for it. Use the right idea or concepts. Yeah, very nice. Thank you.
Thank you. Wait, 7 people on the list bar. In here it says 7 people on the list.
Yeah, that's from the 6. That's from the exactly. We'll speak to exactly 6, 7. So this is continuous. So C and D is under the same setup of exactly. I think that's Catherine's question, right? Yeah.
Because part C and part D also use the condition from part B. So the N would be A. And it says speak to exactly 6 people would be 6 success. Because if the person is rejected to be interviewed, the person won't be able to speak with the interviewer.
Yeah, I think Catherine is okay now.
Okay, thank you.
Thank you, Jia.
Hi,
Okay.
Professor. Good evening.
Yes.
I'm going next, Professor.
Okay.
Professor, can you see my screen?
It's popping up. Yes, now.
I'm going to present question number 85 of chapter 4. An automotive manufacturing company produces brake pads in lots of 100. This company inspects 15 brake pads from each lot and accepts the whole lot only if all 15 brake pads pass the inspection test. Each brake pad is independently of the others, faulty with probability 0.09. What proportion of the lots does the company reject? So solution of this question is probability that a brake pad is not faulty. 1 minus probability brake pad is faulty. It's 1 minus 0.09, which is given in the question. So answer of this is 0.91. After that, we have to find that probability a lot has been rejected. It's equal to the probability at least one of the brake pad is faulty, which is the complement 1 minus probability none of the 15 brake pad is faulty. 1 minus we had then 0.91 to the power of 15. We will get the answer 0.2430. And then after calculation we will get 0.7570, which is 75% of the probability.
Great. Very nice.
Thank you, Professor.
Mm. I really enjoy your presentations, guys. Thank you. Who's going next?
I got number of question 4.87. Suppose that
Okay.
a group of 15 female students is selecting one shop out of the 6 available shops nearby to buy their prom dress. Each student, independently of the others, select shop I with probability Pi, where the sum of 6 to I equal to 1, Pi equal to 1. The first question is asking what's the exact number of shops that will not be visited by any student from this group. It means that x will be equal to 0. This question is a binomial distribution problem. So you plug in, because there's 15 students choosing, so it's 15 of zeros student going to choose a shop, and they were choosing 6 of it, and then 5 out of 6 left. You put it in, you get 0.0649, and for the expected value will be the answer times 15 to get 0.9736. And then for part B, it said that by exact 3 students, you do the same. This time, x equal to 3. Then you plug in a number to get 0.236, and then times 15 to get the exact numbers 3.5438.
They only ask for the expected value for a particular case, huh? Interesting. Okay, nice. Binomial.
Can you see my screen?
Yes, Shuyin.
Okay, so I'm going to present question number 60 from chapter 4. So the question is, suppose that the number of weekly traffic accidents occurring in a small town is a Poisson random
variable with parameter lambda equal to 7. So question A, what is the probability that at least 4 accidents occur until this week? So in here we use the Poisson formula. X, which is represent the number of accidents, and lambda is equal to 7. So the probability of X at least 4 is equal to probability of X greater and equal to 4 is equal to 1 minus the probability of X less than 4. So X less than 4, which is X equal to 0, X equal to 1, X equal to 2, and X equal to 3. So we just plug in all the number into the Poisson formula. Then we will get is equal to 1 minus 0.0818, which is the answer is 0.9182. And B, what is the probability that at most 5 accidents occur until this week, given that at least 1 accident will occur today? So in this question, we use the conditional probability. So the probability of at least most 5 given that at least 1, which is equal to the probability of X less and equal to 5, given that X greater and equal to 1. Then by the conditional probability, which is equal to the probability of 1 less and equal to X less and equal to 5, divides the probability of X greater and equal to 1. So the probability of X between 1 and 5, which is proof that the probability of X equal to 1, X equal to 2, X equal to 3, X equal to 4, and X equal to 5, and use the number into the Poisson formula. Then we will get the answer is 0.2998. And the probability of X greater and equal to 1, which is equal to 1 minus the probability of X less than 1, which is equal to 1 minus the probability of X equal to 0. So the answer is 0.9991. And we just use this, divide this, we will get the answer is equal to 0.3001.
Nice. Nice. Thank you.
Thank you.
1, 2, 3, 4, 5, 6. I have 2 more to go. So 音频 67, right? Can't hear you. Maybe you mute yourself. Are you speaking? Oh, right here, very, very low voice. Yeah, can you increase your volume?
It's good now.
But your voice is very low for us. But the noise sounds big, but your voice is still very low.
Sorry.
Yeah, I think you just move something, and that right, that sound is has a big volume, but your voice has a low volume.
What about now?
Yeah, I think now it's okay.
Okay. So my question is 67. In a central country, babies are born at an approximate rate of 6.94 births per 1,000 inhabitants per year. Assume that the total population is 40,000. Question A, what's the probability that there will be more than 60 births in this country during a 3-month period? So use the Poisson formula. For the lambda is equal to n times p. The n is rate of baby sperm per year is equal 6.94 times 50,000 over 1,000 is equal 277.6, and the p is present the time used, and I is the number of baby sperm born. So question A, the lambda is equal to n times p. The p for question A is 1/4, so the lambda is 69.4, and the probability of I greater to 60 is 1 minus p.
Yeah, just hold on a second. So everyone understand why is 1/4, right? Because question A said 3 months period. So each quarter, the 4 quarters. Yeah, go ahead.
Okay, so the 1 minus p I equals to 60. So the answer is 0.1419. And for question B, what's the probability that there will be more than 60 births in at least 2 phases of 3 months during the next year? And we can use the binomial formula. For the n is equal to 4 because there are 4 phases of 3 months period in a year, and x is the numbers of phases. So for question B, x3 is at least 2, so x3 and all equal to 2. The probability is 1 minus the probability x less than 2 is 1 minus x equal to 0 and x equal to 1. So the final answer is 0.09917. And for question C, if the present season, a 3-month period, is identified as season 1, what's the probability that the first season to have more than 60 births will be season I equal to 1, 2, 3, 4. So for the y is equal to the number of seasons, we can use the geometry formula. When y equals 1, the probability is 0.1419. When y equals to 2, the probability is 0.1218. When y is equal to 3, the probability is 0.1045. When y is equal to 4, the probability is 0.0897. So that.
Okay. All right, thank you. So I think Tom, you're the last one. 1, 2, 3, 4, 5, 6. So
Hi.
hello.
As a disclaimer, I think there's a typo in this question for part B.
Oh.
But I'll just start with part A. Anyway, for part A.
Hold on a second. Let's read the question first.
All right. So part A is given an urn with 10 red, 8 black, 7 green balls. One of the colors is chosen with equal probability, so 1/3. is red, black, or green, and 4 balls are randomly chosen. Let x be the number of balls of chosen color. So we're finding probability that x equals 0. So none of the balls are of the chosen color. So for finding the probability, we take the outcomes where we get no red chosen and no black chosen or no green chosen. So and so you just use combination. It's pretty straightforward for that. And add it together to get probability x equals 0. Okay, so for part B, I guess the typo is well, in the hint it says express x in terms of x1, x2, x3, x4. But for part B, it's not helpful unless the word is R, because it's saying let xi equal 1 if the ith ball selected is of the chosen color, and let it equal 0 otherwise. So if the word is selected is, that means it's just that position is of the chosen color. So it would only help if that word was R. So like if it was, like if x equals 4, then it'd be like the 1, 2, 3,
Yeah, I think
4 balls.
I think the question is just treating I as a certain number. So it's for I equals 1, 2, 3, 4. So
Yeah,
B is like 4 questions.
Yeah.
Okay.
Yeah, it's the last question in the textbook, so I think that's why it has a typo. But I answered it as the textbook, gave it. So we're given, so we have to find xi equals 1, where xi equals 1 if the ith ball is chosen. So I interpreted that if like xi is equal to say 4, that means the 4th ball is the chosen color. So for this,
it's not one of the balls is a chosen color. I equals
since
to 1.
the word is, I just interpreted it literally, where only that position is of the same color. So for the answer for this is, since we aren't conditioning on prior colors being chosen, we simply count the number of colors of the chosen color divided by the total number of ways that the ith ball is the chosen color. So we have just 1/3, which makes sense because whatever ball we choose, there's a 1/3 chance that the color we chose is the same color. Okay, so part C is find expectation of x. So expectation is the sum of the weighted averages, all the values you can take. So from x equals 0 to x equals 4. So similar to how we calculated x equals 0, we're taking combinations of, say, if x equals 1, we're taking 3 non-red, 1 red, 1 black, 3 not black, 1 green, 3 non-black. We use basically combination formulas, and we add up all the weighted averages of x equals 2, 3, 4, and we get 1.3 at the end.
Okay.
So yeah. So I think
to slow down.
well, I think the hint was like they were implying that xi, it says expressed in terms of x1, x2, x3, x4, but the part B, it's helpful if that word was R, because otherwise it's only asking about the ith position. So yeah.
Okay.
It's a bit nuanced.
So
yeah.
So anyone has any questions? Catherine, do you have any questions? Okay. Yeah, if any of you interested in doing this, after class you can try it. Okay, sometimes, right, sometimes I think some questions are interesting, so I will do it myself too. Yes. All right, thank you, Tom. That's everyone, right? Oh, Aya wants to present. 66, I don't remember. Oh, audience did 66. Thank you, Catherine. Aya, you want to try another number?
Yeah, I'm looking. Give me a second.
Okay. You should prepare earlier.
Yeah, I prepared like 25 questions for the today's due homework.
Okay.
Okay, let me do it next time.
You want to do next time? Okay.
Yeah.
All right. That's fine. All right. Thank you anyway. Anyone else like to present? Okay. If not, okay. By the way, I haven't looked at your exam yet. So I'm planning to do this weekend. So today we're going to chapter 5, continuous random variables. So before we were dealing with the discrete. So continuous random variable versus discrete random variables. Discrete means countable, right? We can count how many. You see x equals 1, x equals 2, at least 5, at least 4, things like that. But continuous variable, we won't be able to count anymore, right? But we can talk about in an interval, right? In an interval, I don't know, for 5 minutes, at least 2 minutes, things like that. Okay. So I'm going to read. In chapter 4, we considered discrete random variables. That is, random variables whose set of possible values is either finite or countable infinite. However, there also exist random variables whose set of possible values is uncountable. Two examples are the time that a train arrives at a specified stop and the lifetime of a transistor, right? Like a height, like a weight, right? You know, all those kind of stuff, we have to measure them. They're not discrete, they're continuous. So let x be such a random variable. We see that x is a continuous random variable. If there exists a non-negative function f defined for all real numbers, having the property that for any set B of real numbers, the probability if the random variable in this set of real numbers equals to this. What is this? This is, well, we're going from a finite world or countable world to uncountable world, to what infinitesimal world. But this, what is this? This still have 2 dimensions, right? We can relate this with the sum of the random variables multiplied by its probability, right? You see, B is a set of all those possible random possible values of this random variable. And the f of x, so f of x is a non-negative function f. So basically, you can think that's a probability. There's going to be a probability. Let's see. So we're going to use intervals now. Let me think. I don't really remember continuous. Maybe some of them. But this is just an idea. This is to define the probability, how to define probability on continuous variables. So the function f we're going to call density functions. Okay, density functions of a random variable. So in words, this states the probability that the random variable will be in a set of real numbers may be obtained by integrating the probability density function over the set B. Okay, since x must assume some value, so we must have, because it's a probability distribution, so it has to qualify this condition, right? So all probability statements about x can be answered in terms of f, for instance. So letting B be a closed interval from A to B, we obtain this probability, right? X goes from A to B, including the boundary points, equals to the integral of this. It's not too strange, right? Except the sign of the integration sign, but everything else is understandable. It's similar to the discrete world. The concepts are similar. Okay, so normal distribution. Okay. So we could imagine something like this, right? If you have taken lower level statistic class, you know normal distribution, right? So probability, the random variable goes from A to B equals the area of the shaded region. That's exactly the picture of this. The picture of this, right? And the picture of this is the whole thing, the whole area. It's the area of everything. It's the area of everything. And it's the area under F. Okay. It's the area under F above X. Anyone has any question? Okay. And of course, at one point, there's no area, right? At one point, it's one dimension. So you see this concept, we have to be careful now, because before we're able in discrete world, you know, we do x equals 0, x equals 1, but no more. In continuous random variable, we're talking about area. Okay, the probability is defined over two dimensions, over two-dimension quantity. So at that point, the probability is just 0. In words, this equation states that the probability that a continuous random variable will assume any fixed value is 0. At any fixed number, at any fixed real number, this is 0. Of course, one dimension, right? No area. We need two dimensions to talk about area. Hence, for a continuous random variable, you know, we use this notation: x less than a, x greater than a, stuff like that. X between two different numbers. All right, so we use it. Where x, you know, in the interval. It could be closed interval, could be open interval. Doesn't, you know, change anything. We say interval. We say interval. All right. So we'll talk about the probability in the interval now, because continuous random variables are measurable but not countable. So if the random variable is continuous, is measurable, we have to give an interval. We talk about interval. Okay, let's see an example. Oh, by the way, I didn't finish talking about this, right? So probability of the random variable less than a is the same as the probability of x less than or equal to a. So this is a huge difference from discrete world, right? Because what? Because at one point, the probability is 0. So those two notations exactly the same. But usually we use x less than a, okay, because we don't care to write one more line there. And we use this f of a, and that's from -infinity up to a. Because why? Look at this picture, right? From -infinity, as x less than a is from a to the left, from a to the left. And usually this doesn't touch x-axis. This end curve doesn't touch x-axis. So we are allowed to go to -infinity up to a. Well, if x is bigger than a, that would be from a up to positive infinity. Okay, let's see first example. Suppose the random variable is continuous and with the probability density function given like this. If x is the variable is in between 0 and 2, and it acts as this quadratic function, downward parabola, right? And if you go out of the interval 0 up to 2, it's just 0. So basically, this probability density function is defined on the interval from 0 to 2. And it acts like a downward parabola. So now, what is the value of C? What is the value of C? Remember the probability, remember we have to satisfy this condition. We have to satisfy this condition. Because to be a probability, the 3 axioms, one of it is add up all the area. It has to be 1 to make a probability distribution. So A, we want to find out what is the value of C, and then B, we want to find out the random variable greater than 1 probability. Okay, let's see the solution. So F is a probability density function. We must have this, right? Because it's a probability distribution. So adds up all the area, it can only be 1. So basically the same for this to be a probability, but the area under the curve F has to be 1. Okay, so that means, right? That means differentiate this from 0 to 2 equals to 1. And C is just some number, real number, so we can factor out the integration. Well, integration is easy, right? But power rule for integration. So 4x by integrate 4x, that's 2x squared. Integrate negative 2x squared, that's negative 2x cubed divided by 3. Then evaluate from 0 from 2. What do we get? We get C equals to 3/8. Okay. We still remember integration, right? The simple integration. Let's see B. We want to find out the area of, so just imagine this is downward parabola. Now you can see the function, right? The density function is a 3/8 of 4x minus 2x squared. So it's a downward parabola. So now we want to find out the area when the random variable is greater than 1. You know, something look like this. Downward parabola. 1 may be somewhere. We want to find out the area from 1 up to positive infinity. So we said, okay, let's just integrate this density function from 1 up to infinity. And the function is 3/8 of 4x minus 2x squared dx. And also the function is defined between 0 to 2, because it's a 0 otherwise, right? So we can change the infinity sign to 2. Then the rest is easy. So in the end, we'll get a half. Anyone has any questions? Okay, let's see second example. The amount of time in hours that a computer functions before breaking down is a continuous random variable with a probability density function given as this. Lambda times e raised by negative x over 100. And when x is non-negative, if x is negative, that's 0. Right. When x is non-negative. So what is the probability that a computer will function between 50 to 150 hours before breaking down? 50 to 150 hours before breaking down. B, it will function for fewer than 100 hours. So right, so this is random variable between 50 and 150. This is x less than 100. So first, since it's a probability distribution, so what do we get? We can find the number, right? We can find the number we can use because we're talking about probability. We can use this to find number. So number indeed is 1 over 100. Then we want to find the random variable goes in between of 50 and 100. So lower limit of 50, upper limit 150. So plug in the density function. And hopefully we still remember how to integrate this. Right, then evaluate it. That's about 38%. Anyone has any questions? B, random variable less than 100 hours. So that's from 0 to 100. Plug in, integrate. That's about 63%. Any questions? Okay, let's see third example. The lifetime in hours of a certain kind of radio tube is a random variable having a probability density function. If x is greater than 100, it's this rational function. If x is less than or equal to 100, it's 0. So question, what is the probability that exactly 2 of 5? What is exactly 2 of 5 such tubes in the radio set will have to be replaced within the first 100 hours of operation? So assume that events EI, I equals 1, 2, 3, 4, 5, right? Because we have 5 such tubes. That I such tube will have to be replaced within this time are independent. Right, so we'll find exactly 2 out of these 5. And within the first 150 hours. So let's see how do we solve this. So from the statement of the problem, we have probability of EI equals to, because we only want to consider the first 150 hours, right? So 0 to 150. Then multiply the density function, integrate the density function over this. So then the density function is a rational function. Then we get a probability of even equals 1/3. So the probability of I's tube will have to be replaced is 1/3. Right. So 2 of 5. So finding probability through this probability distribution, the density function. Now the either good now, so have the 5 tubes, right? We want to consider 2 of them are good, 3 of them, exactly 3 of them are good, so 3 of them are bad. So we have this binomial, right? Out of 5, any 2 of them, consider any 2 of them, exactly 2 of them. So that's 1/3 raised by 2. And then the better ones, 2 over 3 raised by 3, we'll calculate that. That's 80 over 243. Any questions? Let's see this one. We have a concept of this cumulative distribution. The relationship between the cumulative distribution f and the probability density little f, right, is expressed by this, because we call this f of a, right? It's probability x is basically is less than or equal to a. That's from -infinity up to a integration of this. Differentiating both sides of the preceding equation, we get. So if we take derivative of both, so derivative of this equals to this. Yeah, so f of a is just a potential function, one of the potential functions of this, right? That is, the density is the derivative of the cumulative distribution function. A somewhat more intuitive interpretation of the density function may be obtained from this. Just want to show you 1.2 again here. So x is in between a fixed one, right? Think about a fixed real number with a little bit smaller than a number or a little bit bigger than a number. Right? So you will use this, if you use this, so that equals to epsilon times f of a. Well, epsilon is very small. Well, f is a continuous function at the particular number a. In other words, the probability that x will be contained in an interval of length epsilon around the point a is approximately epsilon times the density function. Evaluate at a, because we cannot talk about exactly at the point, because at a value, at one value, at a is a 0. So capital letter F of a is a 0. So how do we deal with the situation? We can't do this. We can, put an x in between of very, very close to numbers, right? It's epsilon close. Epsilon is just a very subtle small number. So from this result, we see f of a is a measure of how likely it is that the random variable will be near a. Okay, this is a very mathematical idea. Mathematics will use epsilon to indicate, quantity really, really small. It can be ignored in life, but it cannot be ignored in pure mathematics. Pure mathematics always use epsilon to prove things. Okay, let's see this example. So continuous random variable x, and density function is f, full node x, and then, oh no, let's see. Distribution function f of x, capital letter f, when the density function f, small f, find the density function y equals to 2x. Basically, we want to find the density function for 2x. So we'll define f of y. So basically, this is what we're looking for. Right? Well, we want to find the density function. So we want to find little f y. We can find in two ways. The first way is to derive and then differentiate the distribution function of y. Would be capital letter Y, f y of a is probability of y less than or equal to a. Remember, that's how we would define here. Right. So f of a is probability of x less than a. Okay. So f of a is probability of less than or equal to a equals to, well, y is 2x. or divided by 2. That's the probability of x less than or equal to a divided by 2. So that's just this. Excuse me. So we differentiate. We get little f equals to half of this little f with the input a divided by 2. This half, because when we integrate, right, we don't have to put the half, so we can factor out the 1/2. But the input of little f is a divided by 2. If we use mathematical way, we see this. We see, okay, the little f of a is y in between of a minus half epsilon, a plus half epsilon. Then that's 2x, then we divide by 2 on 3 sides. That's a divided by 2 minus epsilon divided by 4. From there to half of a plus 1/4 of epsilon. And which this is half of epsilon f of x. Okay. Just a little fun question here. Anyone has any questions? I like the first way. The second way is the mathematical way. Very mathematical. Right. The first one is it shows you quite obvious. Okay, let's see. Expectation and variance of continuous random variable. Okay, let's talk about this. Should we talk about, let me see how long this one, 5.2. Let me go back to see how many more we have to talk about. We have chapter 5, we have expectation, uniform, normal, exponential, other continuous, gamma, distribution, Weibull, Cauchy, beta. I don't think we're going to talk about all of those. Jointly distributed random variables. Let me check our syllabus. Chapter 5. Okay, we have for continuous random variable, we have to cover uniform random variable, exponential random variable, normal random variable, gamma, beta, and Cauchy. Okay. All right. Okay, maybe we'll finish halfway. So expectation, expected value, and the variance of a continuous random variable. So in chapter 4, we define expected value this way. Well, of course, finite world or countable world, right? But when x is a continuous random variable, we have a probability defined this way. So now, expectation or expected value, because we don't use, when I learned, we never use expectation for expected values. but this textbook use this. We always call expected values. So expected value equals to this. Negative infinity, positive infinity, little x times f of x dx. You can see this is from, comparing to this, right? From finite world to infinitesimal world. Let's see this example. So we want to find expected value for these density functions equal to 2x. X is from 0 to 1. So basically this function is defined from 0 to 1 and it's linear, right? What do we see? Do you see a triangle? Right, so we see a triangle here. So expected value is this, right? And from 0 to 1, because 0 otherwise. So we just, so x times 2x, that is 2x squared. We anti-differentiate. We get a 2x cubed over 3. From 0 to 1, that is 2 over 3. Okay, just like the idea is the same, the concept is the same. We just have to change from countable world, countable world to infinitesimal world. Let's see this B. The second, the density function is given by this. It's 1 from 0 to 1. And the 0 otherwise, what do we give? What are we given? We're given a rectangle, right? Because continuous random okay, let me go back actually. I was talking about, I hope you see this is a triangle, right? Just draw a picture on your head, draw the plane on your head, and this function density is 2x, right? It's 2x. It's a linear function with a slope of 2. So this line, we can drop a vertical line to x-axis. So the area of the triangle will be 1. The area of the triangle will be 1. Right? Then we could ask questions, okay, what is the probability of x? Because this is defined from 0 to 1. What is the probability of x less than half? Or maybe x greater than quarter? Stuff like that. And what is that? That's just part of the area of the triangle. So similarly for this one, can you picture a rectangle? Because from this 0 to 1, your function value is 1, constant function, polynomial of degree 0. Right? You drop 2 lines to x-axis, so you see rectangle. And the area of this rectangle is 1, because we are in the probability world. And we're going to talk about it. That's called uniform distribution. Anyway, let's see this one. So what do we want to do? We want to find expected value of e to the x. Okay, I is asking a question. When x equals to 2/3, the area of the triangle to the left is equal to the area to the right. Oh, okay. So you mean x equals to 2/3? That's halfway. Oh, I see. Okay. Good thinking. Good point. Thank you. Okay, so we call e to the x y. Let's define f of y, the cumulative distribution function of y. Okay, by the way, everyone see the difference of the capital letter and the little letter, right? The little letter f is the function, the density function. Capital letter F represents the area we're looking for, the probability we're looking for. So that's why it's called a cumulative distribution function of y. So for x goes from 1 to e. X goes from 1 to e. Oh, here, right? Because now inside this expectation, we want to find the e to the x. E to the x. So the random variable now goes from 1 to e. Okay, so define f of y. So we define f of y for this. For y, so maybe we should use y. I think here we should use little y instead of x. But anyway, so f of y of x equals the probability of y less than or equal to x. That's the definition of f, okay, cumulative distribution. So that means probability of e to the x less than or equal to x. We'll take logs on both sides. That means the random variable x is less than or equal to log of x. I think this log is a natural log. Okay, it's not a common log. Usually we just use ln. And what is the definition of this? Definition of this is just the integration from 0 to log x, then f of y. Yeah, I like this, f of y. Okay, f of y dy. Then if we do that, if we integrate this, we get a log x. So by differentiating fy, we can conclude the probability density function for y is 1 over x, right? Because we differentiate this capital letter F. So that's how we find this. So fy of, I hope they use y for this little x. It would make better sense. Okay, y, this is, okay, anyway. So this is a cute question. Anyone has any questions so far? Okay, let's finish it. So we want to find the expected value of that, which means we define y. So by definition, that's from negative infinity to infinity, x f of y. But y is in between 1 and e. Right, so the 1 and e, we differentiate. We differentiate x times 1 over x. X times 1 over x, that just becomes 1, right? So the fy of x is 1 over x, x times 1 over x, that just becomes 1. That's why we don't have any integral in here. So that's just e minus 1. Okay, this question is cute, isn't it? Anyone has any questions? All right, let's do this one. If x is a continuous random variable with probability density function, for any real value function g, so expected value of g of x is, because the variable now is g of x. That's why, so the expected value is g of x times f of x. So an application to this yields, if we use this, so e to the x, we just use the e to the x multiplied by f of x, right? But f of x is defined as 1, so, and x is going from 0 to 1, so that's e minus 1. Okay, so this is so useful. This proposition is useful, right? So for this question, so now we can use this proposition to deal with these kind of questions, right? Let's see this lemma. This lemma is saying for non-negative random variable y, expected value of y is integrated from 0 up to positive infinity, probability of y, capital Y greater than little y dy. So let's see. We present a proof when y is continuous random variable with a probability density function. So this one would equal to probability, because probability of y greater than y is this. It's an integration from y up to positive infinity, f of y of x dx. Right? So with this double integral, right, that's the probability of y greater than y. Interchanging the order of integration. I guess dx, dy, right? There's no independency, I guess. Okay, so no independency, so we can switch, you know, freely. Then we can put this one. Oh no, there's something, right? So we integrate x direction last. We integrate y direction first. So y direction, okay. So dx, this is a y. So we see x, y equals the x line, right? So y equals the x line. But this is from y to infinity, this is from 0 to infinity. So from y to infinity versus from 0 to x dy, right? So the relationship, we still remember this, right? We still remember this. So we integrate dx from y up to infinity can be changed to this dy from 0 to x. Then what does this give us? From 0 to x1, that's just x minus 0, right? Just x. So that's expectation of y. I see. This is Q proof. It's Q proof of this lemma. All right. So expected value of y equals to integrate from 0 up to positive infinity of the probability of y greater than the random variable than dy. Okay, this is another proof by using g of x. Right, that's by definition, that's this. Then what is the probability of this? That's this. Change the order of integration, similar. Okay, one more example. Or maybe we can finish. Yeah, we can finish. The stick length 1 is split at a point u having density function f of u equals 1, u from 0 to 1. So that's it. So basically the function, again, uniform distribution. So you imagine a rectangle. Determine, actually this is a square in this case. Determine the expected length of the piece that contains the point P for P in between of 0 and 1 and can be 0 and 1. So let's see, let LP of U denote the length of the substick that contains the point P. And note that LP equals to U if U is greater than P. Okay, U is a point. Okay, U is a point. U is a point, okay, and so if the stick is split at point U, it would have this density, right? So, but then this denote LP, so let LP denote this. So define it as U if U is greater than P. Okay, if U is on the greater than P. And 1 minus U if U is less than P, all right? Then we can use the little lemma or the proposition saying, okay, expected value of LP, right, is defined from 0 to 1. LP of U, so we split it into two parts, right? Because at point P, we'll have two, we'll have this, right? If it's greater, if U is U greater than P, that's U, right? So if the point is greater than P, we have this part. If the point is less than P, from 0 to P, So we have this. Then the rest is just calculation. Right? The rest is just calculation. So in the end, you'll get a half plus p times 1 minus p. Right? A quadratic equation depends on p. So let's see this. So this is p, this is u. Right? If u is greater than p, we have this b. If u is less than p, we have this 1 minus u. So little mark. Since p times 1 minus p is maximized when p equals to half, it's interesting to note that expected length of the substate containing the point p is maximized when p is the middle point of the original state. Anyone has any questions? Okay, let's see this one. I think this is second to the last. Oh, we still have a couple more. Suppose your estimate is early for an appointment, then you incur the cost CS. And if your estimate is late, then you incur the cost of KS. Suppose also that the travel time from where you presently are to the location of your appointment is a continuous random variable having probability density function f. Determine the time at which you should depart if you want to minimize your expected cost. Because if you go early, it costs you CS. If you go late, it costs you KS. So let X denote the travel time. So if you leave t minutes before your appointment, then your cost, call it this, Ct of X. So density function is given as this. C times t minus X if X is less than or equal to t. Ct, right? Because X is travel time. So this is saying if your estimate is late, right? That's CS. So that's why we have here. So t minus X, because X denotes the travel time, right? If you arrive early, you got this one. So t minus X times C. Then if you are late, right? If you're late, you use more time. If you're early, you use less time. If you're late, you use more time. So that's X minus T times K. And this is for X greater than T. This is for X less than T. So therefore, expected value of this, excuse me, two part, right? From 0 to T. From 0 to T, that's a C times T minus X times the density function. Then from T until past infinite, that's K times X minus T times the probability density function. So we could do a little bit of calculation. So we can factor out CT from here, because CT is just some numbers. And also we can factor out KT. We have KT, this one. So what's left is from 0 to T, differentiate something cancelled, isn't it? So we have CT f of X. We have CX, negative CX f of X. Oh, we split. Okay, so that's this part, the first part. Then this is the second part of this one, negative CX, CX f of X. Then this will have two parts. So K times this, and minus KT times this. So the value T that minimize this can now be obtained by calculus. Right? So differentiate this, differentiate that, we get CT f of T from the first one and differentiate this one, we're going to see f of t, because this goes from 0 to t, right? The cumulative, so let's see capital letter f of t. And for this one, it's going from t to infinity, so that's kt f of t. Kt that's from this. Then from this one, what do we get? We get k t f of t, and from this one, or this one we get a kt f of t, right? This one we get a negative kt f of t, and k f of t minus 1. From this one, we get minus k f of t. Okay, where did we get this? Ct because this part is just a probability of greater than t, the random variable t greater than t, which gives oh, okay, they play the trick. You see, this is negative is here, it's hiding here. Okay, it's hiding here. So if we don't do negative, so that should be k f of t, then minus k. All right, then simplifying, we get a k plus c f of t minus k. So now, equating the rightmost side to 0 shows that the minimum expected cost, yes, is obtained when you leave t star minutes before your appointment, where t star satisfies k over k plus c, right? Because if this is 0, so f of t will be equal to k divided by k plus c. Okay, cute. Anyone has any questions for this? It took me a while. Okay, let's see this example. If A and B are constants, then expected value, so this is corollary. I think x is same as before. Oh, different. So if A and B are constants, so expected value of A, or same as before, ax plus b equals to A times e of x plus b. Yes. And for variance is a little bit different. Variance of x is defined as expected value of x minus mu squared. Mu should be the mean. Mu, let's see. Mean, expected value of mu. Okay, then, or can be written as before. Right. Okay, let's use this formula to find variance of x for example 2a. First, let's calculate expected value of x squared. That would be x squared times f of x. F of x is 2x, right? So we'll get 2x cubed. Integrate that, evaluate at 0 and 1, we get a half. Then e of x is 2 over 3, we square that. So variance is just 1/18. And we have this variance of ax plus b equals a squared variance. Just ignore the b. This is the same as before. This is the same as a discrete. Okay, that's it. So next class we'll talk about the uniform random variable. Anyone has any questions? Let me stop recording.